All right, testing one, two, three. We're on a 10-second delay here, so I want to make sure it works before we continue. All right, that sounds a lot better. Just had to restart. Anyway, back to the knapsack problem. Where was I? All right, so remember last time we were looking at a greedy approach where you just take the most valuable items first. But if that happens, then you end up with a weight, only a value of 25. You can only take the first two items. Whereas if you had not been greedy about it, and you had foregone, let's see, if you had foregone the third item here and waited and went and took the last item, then you'd have an even better solution, which is actually the optimal solution in this case. So that was the 0, 1 knapsack problem that we introduced last time. What I want to do now is I want to look at a backtracking solution. And what I mean by that is, first of all, we're going to note here that you can go ahead and solve this in a brute force manner by simply generating all possible subsets. Generating all possible subsets and taking the best solution among all feasible solutions is possible. But say that you have 100 items. That means that you are going to be generating 2 to the 100 subsets, which is not going to be practical at all, and that's not feasible at all to do that. You would generate one, look and see, is it feasible? Does it fit in my knapsack? Yes? Okay, well, if the answer is no, then you throw it out immediately, look at the next solution. Otherwise, you would say, yes, it is feasible. Okay, well, what's its value? Its value is 25. Okay, what have over here I've kept track of the best solution so far, and it had a solution of a value of 15, right? 25, well, that's better. So throw out that other solution, and now I've got this solution over here. So keep going until you find the best solution. Until you've examined all solutions, and then once you've examined all solutions, thrown out the infeasible ones, and selected the best one, then you've solved the problem. You've optimized your knapsack. Unfortunately, that's a really, really naive way of doing it. Because what if, the vast majority of them are infeasible? For example, again, over here with the example that we were running yesterday. It's infeasible to take everything because that would not work with our weight capacity. When we took the first two and then we considered taking the third, that would have exceeded our weight capacity at 9, right? So if you consider generating all possible subsets and you're going down in this computation tree, here's that infeasible solution, that being greedy that we wanted to examine. Right? Before I even go down that path, I could say, well, that's not going to work because taking that third item there, that's going to exceed my weight capacity. So I'm not even going to go down that path because certainly if these 3 items don't fit in my knapsack, these 4 items certainly do not, right? So I'm not even going to go down that computation path. Now, this is a small enough example that it doesn't look like that big of a deal to just cut off this computation branch. But you can imagine if it were a much larger input, say 100 items like I was talking about before, then this would be a huge computation tree hanging off of this otherwise large tree, right? If we prune that entire thing off, then we could effectively cut out, say, 50%. 75%, 90% of all of the possible solutions, right? So how do we go about doing that? That's called, first of all, I want to talk a little bit about what that kind of technique, that general technique of that general approach is called, because it is valuable. We're going to be using it now several times. It's called backtracking. Let me transition over here. Sorry. There we go. So generating combinatorial objects is blind problem solving, right? You are naively looking at every possibility. You're not taking any other factors into account. You're not taking the structure of the problem into account, or whether or not building these iterative solutions, these partial solutions. If it's infeasible, then if you build on top of that solution, then it's also going to be infeasible, right? That's a structure of the problem that you can exploit so that you can reduce the amount of computation time and resources that you need to solve the problem, right? We often need to take structure into of the problem into account, right? We like structure, right? It can be exploited for more efficient solutions, right? And that's where backtracking comes in, right? Brute force algorithms, you don't need to consider. You may not need to consider a large proportion of possible solutions, right? You can cut them out and you prune it out in your computation tree or whatever however you're trying to visualize the problem. So the general technique here of backtracking is that you iteratively, now not iteratively, necessarily iteratively as in a for loop or a while loop, but partially, right? That is, or recursively, which is what we're going to look at. Build a partial solution until it becomes infeasible, in which case you backtrack to a previous partial solution, right? And then you try a different path, right? And you've probably seen that you even as a kid you would have used this technique, right? Walking around a maze, right? Once you hit a dead end, you backtrack, right? And you try a different path. In a maze, if you've got a left or a right, a choice of a left or right, then you backtrack, and then you go to left. You hit a dead end. You backtrack, and okay, well, I should have taken a right in there instead, right? You try up all possibilities to get out of the maze. Right? Chess is another example. Computers look, computer or AI. It's kind of generous to call them AI, artificial intelligence, because they just use heuristics. AI players will look ahead, right, to a huge portion of possible moves and choose the best path, right? Computers are cheaters because they can look at millions, billions, trillions of possible moves into the future of the game, whereas we humans, we can only look about a few moves ahead. The best chess players, of course, can do dozens of moves ahead, but the best chess players use general strategies, right? An AI computer doesn't necessarily do that. It just uses heuristics by looking ahead. Oh, no, I'm going to lose if I make that move. Or I have a 90% chance of losing if I make that move. I'm going to backtrack and I'm going to make that other different move, right? So how does that work with respect to the knapsack problem? The way that we're going to do it is we're going to take that algorithm that we developed and in fact programmed last time, and we're going to iteratively build a solution. We're going to start with the empty set here up at the top, and then we're going to consider adding, well, what if I stole item 1? What if I stole item 2? What if I stole item 3? What if I stole item 4? Right? Well, stealing item 1, well, that gives me a certain value, and it is feasible. Okay, well, now that I've stolen that, then I need to choose my next item. You can choose the second, the third, or the fourth, right? And at each point you ask, is this feasible? If it's feasible, okay, I'll go ahead and consider that. And also, what is its value? If its value is greater than what I've found so far, the best solution that I've created so far, then I'm going to go ahead and make that choice and update my best solution. But once I hit a dead end here where there's an infeasible solution, I say, okay, well, that's not going to work, so I'm not even going to bother examining any other subset that contains more items. I'm going to backtrack. Keeping in mind that I've got this best solution over there, I'm going to try a different choice. What if I had stolen item 4 instead of item 3? Right? And that's the basic idea for backtracking. We're not going to program it because, of course, that is your assignment. But we are going to give you the general pseudocode for how to go about doing this. Basically, it's going to be this exact same algorithm that we developed before to generate all possible subsets. But at the same time, we're going to keep track of, is this a feasible solution? If not, don't bother recursing on it, right? And what is the best solution that we've found so far? So to do that, we're going to need a lot more in our input. And the pseudocode is available fully in the lecture notes if you want. I'm just going off of that. But I'm going to describe it line by line as we go. The input is going to be an instance of a knapsack problem. A knapsack problem. And that's the elements, the actual items, the weights, the values, and of course your capacity. Yesterday I called it W. I'll go ahead and go with the pseudocode notes here of using K as my capacity. A big K, right? In fact, yeah, I don't like that. Let's just go ahead and go with big W here. All right. And you're also going, because we're iteratively building this, because we are going recursively here, what we have is a partial solution. We've got a subset of the set of items. All right. So a partial solution, and that solution I'll just label as S, which is a subset of A, right? Consisting of elements of A not indexed more than J, right? Remember J, we were using that index last time when we built this algorithm to keep track of what have we considered so far. I'm going to go ahead and take the first item, but I'm also going to tell the function that I recurse on that I've considered items 1 through 1. When I recurse down here, I'm saying I've considered items 1 through 2. I decided not to include ace of 1 in this computation path, but I did include ace of 2. Over here, I would pass in j is equal to 3 because I've considered all items 1, 2, and 3, but my choice was only to take 3, right? We need to keep track of that so that we're not repeating things, repeating solutions over here, right? If I don't pass in that index, then, oh, A3, well, what about A1, A2, and A4? We're not going to consider A1 and A2 because we've already considered them over here in this computational path. So we're going to have to bring in this index j here to indicate that we've considered everything 1 through j. Right? Don't consider those things anymore. Consider all the rest of the elements in the knapsack problem up here. Okay, and our output is going to be a solution at least as good as S. All right. We're given a solution that has some value, right? We're not going to replace it with a solution that has a less value. We're not going to replace it with a solution that is infeasible. So if we get to a point and we say in the recursion and we're given a solution, okay, well that's a good solution. There's no other solution that's feasible. There's no other solution that's better than it. We're going to end up giving you your solution back, right? And ultimately, though, when you kick this algorithm off, you're going to end up with the best solution among all of them, but the best feasible solution among all of them, okay? We need a good stopping point. So if j is equal to n, then we're going to stop, return s. We're going to end up returning the solution that you gave us up here, right? Why? Well, because the index here is tracking what elements you've considered. I've considered elements 1 through j. Well, after you've considered elements 1 through n, there are no other elements to consider. You're done. You've reached the end of your recursion. Over here, that would correspond to this computational path down here. And this computational path down here. You've hit A4 and you've included it. There are only 4 elements. There's not a 5th element over here, so go ahead and return. Likewise, here, 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 here. In other words, all of the leaves of this computational tree, you have to have a stopping point somewhere. So once you get to that stopping point, just immediately return. There's no other solution to even look at. All right. Otherwise, we're going to consider the best solution among all of the other solutions. If you want to look at this more generally, we've come in to this computational node basically, and we've been given this solution S as input. We're going to consider a possible solution over here, a possible solution over here, a possible all these possible solutions. And we're going to look at all of them, and we're going to select the best one. If none of them are feasible, then of course we go ahead and go with S. All right? So we initialize the best solution to simply be the solution that we were given, right? Because we have to have at least one solution. Now I'm going to consider all of those other elements. For K, running from J plus 1, remember we've already considered elements 1 through J. Now we need to consider elements J1 through N. We're going to do the following. We're going to take our partial solution and we're going to add this. This is our partial solution right here. And what I'm going to do is I'm going to add the kth element. Right? Again, that corresponds to me coming down this this computational tree, and you can add 2, or you could add 3, or you could add 4. So that's what this for loop is doing. Right? I've relabeled this here, so it's S prime. Before, when we actually programmed this, we added it, and then after we came back from the recursion, we took it off. I'm just relabeling this as S prime so that I don't have to worry about those details. Of course, you could do a deep copy and then add it so that you don't have to take it off of the original, right? So that you're not changing the original. Those are all things that you have to consider when you actually go to program this in whatever programming language you're going to use. We need to check that that it's feasible. If the weight of S prime, WT for weight, is less than or equal to W, remember that is the weight capacity of our knapsack, then it's a feasible solution, right? It's feasible. So we check it, right? What we're going to do is we're going to continue our recursion here, and I'll just use T here as another solution. I'm going to call this method or function or whatever recursively, passing in the knapsack problem here. I'll call it K. K, okay. And the partial solution S, and then lowercase k here. I'll call this KS so that we don't confuse K and KS, right? Again, what I'm passing in here is the instance of the knapsack solution, knapsack problem, because you need the items, you need the items, you need the weight, you need the value, and you need the capacity. You could make those into global variables. Globals are evil. Or if it's more object-oriented, you could create a class that represents and encapsulates all these things or whatever. We just need to pass those things. Or you could pass them all individually. You could pass it as a list, and a number. Right? It doesn't really matter. What we're going to do is we're going to pass in that partial solution. Excuse me, that should be S prime that we just created. This partial solution, we're going to pass that in, but we're also going to pass in K here because remember we need the K is going to end up being our J. We need to track what have you considered. I've considered elements 1 through K with respect to this loop. Don't consider them again, otherwise you'll be repeating work and you won't be making progress towards termination of the algorithm, right? Once we've done that, we check, is it better? If the value of T is greater or equal, if you want, you can break ties arbitrarily, it doesn't matter. The value of the S best that you found so far. Remember, we just returned from the recursion here. This recursion gave us the best possible solution, considering everything down that computational path. We're going to go down this computational path, and this when you come back from the recursion, it gives you the best possible solution. It could be giving you your solution back if there is no better solution or no feasible solution, but that doesn't really matter, right? We'll just go ahead and update sBest to t if its value is greater. And great, I fit it, right? Otherwise, actually, no, I didn't. There's one last thing here. We'll return sBest, okay? Because we're considering all possibilities in our recursion here. Analysis on this algorithm is going to be the same. Ultimately, if all possible subsets are feasible, you're going to end up examining all possible subsets in order to get the best one, right? Because this is an optimization problem. You're trying to find the best possible knapsack solution. So it's going to end up being, in the worst case, order, 2 to the n, right? Because that's the number of possible subsets of a set of size n. This is only a heuristic, right? You could end up cutting out half or 90% of all possible solutions, which is why it's feasible to do this on in an actual programming setting. We've constructed small enough test cases or test cases such that a lot of the solutions are infeasible and you end up cutting them out so that it will actually run within your lifetime, right? But otherwise, if you had 100 items here, that's not running with respect to the heat death of the known universe, much less your lifetime. So it's just a heuristic in that you're cutting things out, you're exploiting some structure of the problem, but there might be problem instances in which that structure fails you, and you end up having to examine all possibilities, right? Because they're all feasible. Now there's a tightrope situation there, because if you look at them, if you pre-process the input and you realize I can take everything, then there's no reason to even run this algorithm and consider every single possibility, because we'll just take everything, right? That's kind of a trivial instance, a trivial input to this problem. Okay. Our program should read from files, right? Yes, generally. The instructions are in the handouts. In fact, you could get started by writing your parsing functionality now for all of the problems and getting those into whatever form you want. If it's a class instance of the knapsack problem, or if it's just a bunch of lists or whatever, you can do that right now and troubleshoot and make sure that it actually works. Okay. All right. No other questions? Let me check YouTube. Nope. Okay. All right. So let's take a look at another problem. So here's a graph, right? And what we remember that you can do paths in a graph, right? You can go from A to D to B here. That's a path of length 2, right? You can go A to B to D to back to A. That's a path, but it's also a special path called a cycle, because you end up back where you started, and it forms a loop, forms a cycle. You can go A to B to C to E, and then back to C, and then over to F. That's not a simple path. That's a complex path, if that word suffices. We're not going to consider those, all right? So we're considering paths here. You can go A to B to D, but then you're kind of at a dead end here, unless you want to go back to where you came from, and then you've formed a cycle. There's a very special type of either path or cycle called a Hamiltonian path. I can go from A to D to D, A to D, B, C, E, F. And you'll note that with this path that I've created, I have visited every node exactly once. Right? I could do that in several other ways. I could go from, D to A to B, then to E, C, F. That's also a Hamiltonian path, right? There's something called a Hamiltonian cycle, where you go out, you visit every single possible node, and then you end up back where you came from. That's a Hamiltonian cycle, right? some of these, making certain choices may mean that you don't have a Hamiltonian path or cycle. For example, if I go from A to B to D, I'm at a dead end. There's no way that I can get over to the rest of this graph in order to explore it. So that won't work, right? In fact, let's go ahead and map our possibilities out here. Yeah, I'll use black here. All right, what if I started at A? Right? Then I've got a few choices, right? I could go to B, or I could go to D. Right? I could go to B, or I could go to D. Right? Suppose that I went to B. Right? Yeah. Then I've got a couple more choices here. From B, I could go back to A, but that's not a simple path because I'm traversing something again. I could go to D, or I could go to E, or I could go to C. Right? So my choices here are C, D, E. Right? Let's suppose that I've chosen to go from A to B to C. Right? There we go. I'll go ahead and color that. A to B to C. Right? Is it possible for me? I've got the rest of the graph to explore here. What are my choices? But is it going to be possible to get a Hamiltonian path out of this thing? If I start at C, if I'm at C here, coming from A to B to C, I've got two more choices. I can go to E, or I can go to F. Right? I can't backtrack though to B. Excuse me. Why? Because that would not form a simple path. So let's continue. If I'm at E, then I have one more choice. I could go over to F. And likewise, if I'm at F, I could go over to E. Right? Now, are either one of these paths from A to B to C to E to F, A to B to C to E to F, does that form a Hamiltonian path? No, because we've left out D. Likewise, does going from A to B to C to F to E, does that form a Hamiltonian path? No, because we've already exhausted all of our possibilities. If we go to C and go to B to try to get back to D, no, these things are things that we've already visited. And I don't want to visit them more than once. All right? So, both of these computational paths here in this tree have led to a failure. There's no Hamiltonian path here. There's no Hamiltonian path here. Right? I'm not going to draw out the entire tree here, but you can imagine that you will eventually find success. If you go from A to B to D, or sorry, let me go to A to D to B to C to F to E. That's another one, right? Then that will correspond to some other computational path in which you chose D instead, and then you went to B, and then you went to C, and then you went to F, and then you went to E. And how do you know that you were successful in that endeavor? Well, look at the depth of this tree. 1, 2, 3, 4, 5. Right? There are 1, 2, 3, 4, 5, 6 vertices. Any Hamiltonian path will have a length of 5, a number of vertices minus 1. And I've gone to a depth of 5 here, so I know that that's a Hamiltonian path without even looking and verifying that all of these nodes have been visited. Right? So at that point, I find success, and I say, yes, there is a Hamiltonian path in this graph. Or no, there's not a Hamiltonian path in this graph. There are plenty of graphs where there is no Hamiltonian path. Right? I won't bother with a counterexample. I'll leave that as a practice problem for you. All right. Okay. So let's write down some notes at least of what we've been looking at so far. So Hamiltonian path cycle. A Hamiltonian path or cycle is a path or cycle in a graph that visits every, in fact, I'll say it's a simple path that visits every vertex exactly once. Right? This is actually a very difficult problem. It's a part of a problem space called NP-complete problems, which we will get to by the end of this course, or NP-hard problems, whatever. And there's a similar problem. I'll take this moment here nobody knows how to do solve this problem in polynomial time. Not even like an n-squared infeasible algorithm is known for this. All algorithms that are known for this are exponential, right? Exponential algorithms, like 2 to the n or whatever. There's a similar problem called the Euler path problem, whereby it's only a slightly different statement. An Euler path is in a graph visits every edge exactly once. And that's actually an easy problem to solve. All you have to do is go through and make sure that that the degree is even of all vertices in the graph. So slight variation. One becomes super hard. One is super easy, right? And that's just the nature of problems. Remember, we like structure because we can exploit structure. And that's structure that can be exploited. That if you want vertices, that's one problem. If you want edges, that's a different problem. And you can exploit the structure of that using math, using Euler's theorem, etc. to say, okay, well, here's a really easy solution. All you have to do is check vertex degrees, right? Really cool that some problems, only a slight variation on a problem can lead to a blow up in the complexity of that problem, right? Let's see. We've got enough here. So let me go ahead and give you some definitions here before we continue. Just making sure that everybody is on the same page here. That an undirected graph is represented by a vertex set, and we usually label these as V1 through Vn, so that there are always going to be n vertices, and a set of edges E, right? A set of edges E in an undirected graph are an unordered tuple. U and V, they're connected by an unoriented edge. That means you can go from U to V or V to U. It doesn't matter, right? Go back and forth. Directed graphs, you can only go one way, and that would be an ordered pair. The neighborhood of a vertex, denoted as ends of V, is a set of vertices connected to it by a single edge in an undirected graph. So that I'm just introducing and reminding you about this notation and this terminology, because we're going to actually use it in our solution here. And then finally, we already defined a Hamiltonian path or cycle is one that visits every edge, vertex exactly once, right? There are other variations, right? And at this point, I'm going to introduce the idea of decision problems versus optimization problems, right? The knapsack problem was an optimization problem. We weren't just looking for a solution. We were looking for the best solution. The decision version is the version that I just gave you. It's a yes or no question, right? Does a solution exist at all? Yes or no. Is this graph a Hamiltonian graph in that it has a Hamiltonian path? Or no, it does not have a Hamiltonian path, right? That's if you put on your programmer's cap, you can think of this as a function that returns yes or no. It's a Boolean function. Yes, there exists a solution. What's the solution? I don't know. You didn't ask me that. You only asked me whether or not there was a solution. Boolean, true, there is a solution. False, no, there is no solution, right? What you want, if you want to actually construct a path, is the functional version, right? Given a problem, if a solution exists, output it, right? So in the context of a Hamiltonian path problem here, we don't want to know just yes or no, there is a Hamiltonian path, or no, there is not a Hamiltonian path. But if the answer is yeah, if the answer is no, we can't do anything, right? There's no Hamiltonian path, so there's no Hamiltonian path to output. But if the answer is yes, then I want that actual path. There might be many, as we already saw in the example. We drew at least 2 or 3 different solutions. I want a solution, right? You can take that further and look at optimization problems. among all feasible solutions, output the best one. And best being, you know, whatever version of the problem that you're looking at. With a Hamiltonian, the knapsack problem, it was the one with the highest value. With a Hamiltonian path problem, it could be a weighted graph. All the edges have a weight. So there might be 50 or it might be a complete graph in which every a permutation of, spoiler alert, permutation of vertices is a valid solution. I want the best one. I want the least weighted one, right? That's an optimization problem. You can also have a counting problem. How many solutions exist, right? So with our input that we had before, with our example over here, how many Hamiltonian paths are there? A lot, probably. And you could to count them up. And again, a naive solution would be go through all possible solutions. If it's feasible, increment a counter. There's another Hamiltonian path. There's another Hamiltonian path. There's another Hamiltonian path. And then once you've examined them all, that's not a Hamiltonian path. Don't increment the counter. Once you've examined them all, you've got your answer to the counting version of that problem, right? So how do we go about solving this Hamiltonian path problem, right? The naive solution is to generate what kind of combinatorial object, right? Are we talking about subsets here? Nope. Because if you're talking about subsets of vertices, right? If I've got, how many did I have before? I had 6 vertices. If I only selected 3 of them, there's no way that I can traverse all the other 3 just using these 3. I have to involve all of them. So I have to choose all of the vertices to begin with. But what kind of combinatorial object are we looking for here? Right? Well, let me go back to the example here. And instead of looking at this tree, let's look at, well, what if I wrote them all down? What if I wrote A, B, C, D, E, F, right? What does that correspond to? That corresponds to the following path. Go from A to B to C to D. Oh, nope. You can't do that because there's no edge there. Okay. All right, well, let's try a different ordering of vertices. What if I went A, B, C, D, F, E? Right? Same problem there, exact same problem as before. So let me just go ahead and randomize this. C, F, E, A, B, C, D. There, that's the one I was missing. All right, well, what does that correspond to? You start at C here, you go over to F, you go over to E, and then you jump over to A. Nope, that's not a solution either, right? So, what are these things? These things are called permutations. That's the combinatorial object that you want to start generating if you're going to go with the naive solution. Just to make sure that we're all on the same page, let's go ahead and review. Suppose that I have, say, 4 elements, A, B, C, and D. Actually, no. That's too much. I don't want to write that all down. So let's say that we have 3 elements. A permutation is an ordered arrangement of elements, right? So if I've got A, B, C here, another way of writing that down is A, C, B, right? This is in contrast to the combinations that we were looking at yesterday, subsets, in that sets and combinations are unordered. This is ordered. Here, order matters. Permutations, order matters. Combination, order does not matter. Right? We could also start with B, A, C, B, C, A. Or we could have started with C and gone to A and B, C, B, A. Right? Each one of those is a permutation. How many of them are there? 3 factorial. So in general, there are n factorial permutations of a set or collection of n elements. Okay. So let's think about the naive solution and how do we go about generating all these permutations. Okay. For that, let me go ahead and check for questions. Nope, none yet. Okay. All right. I'm going to show you a way to generate permutations iteratively. Okay. So let's go back over here. All right. Generate permutations. Okay. So generating permutations. Sorry, it's slowing down for me now. Hopefully it's not bad for you. We've got 0 drop frames, so okay, fine. So here's the outline. You start with the identity permutation. And again, just like with combinations, we're going to go with permuting numbers, 1 through n, which can be used as indices for whatever you're actually trying to permute. If you've got 4 people, Alice, Bob, Oscar, and Jane, and you want to arrange them in a photo, how many ways are there of doing that? 4 factorial. Well, all you need to do is go, instead of Alice, Bob, Jane, etc., you can go with 1, 2, 3, 4, and then associate 1 with Alice, 2 with Bob, etc. And then once you've permuted 1 through 4, then of course that you can map that back to the objects or the things that you are actually permuting to get an arrangement of those objects. So we're going to start with the identity permutation, which is 1, 2, 3, 4, ... n. Right? And my LaTeX is now working. Right? Given the current permutation, A1, A2, ... A n, we want to find the next permutation. Right? So again, this is going to be iteratively. This is just like our first solution for the combinations problem, generating combinations. This it's not going to be recursive. Okay. What we do is we find the rightmost, that is last, pair of elements, AI and AI plus 1, such that the following inequality holds. A sub I is less than A sub I plus 1. There we go. Excellent. Once we've found that pair, we find the smallest element to the right. That is, we call that the tail of the permutation, larger than A sub I. Call it A prime. Okay? Then we do 2 operations. We swap A prime and A sub I. And then we order the elements to the right of A prime. Right? So that's the outline. Let's take a look at what it looks like within an example. All right, I'm not going to do it. I'm not going to start 1 through n. I'm going to start I'm going to jump right in the middle of the algorithm. All right. So let's go. The example I've got here is 1, 6, 3, 5, 4, and 2. Right. In other words, over here, n is equal to 6. We're looking at all permutations here. Now, if I started at the beginning to get to something interesting, it would take a long time. Why? Because there are 6 factorial, that's 720 possibilities. So what I've done is I've jumped into the middle of the algorithm here where I've got the following permutation. Okay? And what I want is the next permutation of elements. So again, I could go ahead and go back. What we need to do is we need to find the rightmost pair, the last pair of elements, such that A sub I is less than A sub I plus 1. So let's go ahead and consider these two. Right? Let me go ahead and write it down so that we have a reference to it. Find last pair such that st A sub I is less than A sub I plus 1. Right? In other words, I'm just looking at contiguous pairs here. 4 and 2, 5 and 4, 3 and 5. And I'm starting at the right and I'm working my way left. Okay? That's why I'm finding the last pair. Well, let's consider this. 4 and 2. Is 4 less than 2? Nope. That's not it. 5 and 2. Is 5 less than 4? Nope. or sorry, 5 and 4. Nope, not those two. 3 and 5. Is 3 less than 5? Yes. So there's my first pair. There's my pair. 3, 5. All right. So 3, 5 is the last pair. Again, I started at the right and I started working my way left here. That's the last pair such that this inequality holds. Okay. Go back. Now that we've found it, now that this is, I'll observe here that A3, sorry, A2, 1, 2, yep, A3, A3 and A4, which is 3 and 5, right, are the last pair. So in other words, A3 is my AI. That's the thing I'm looking for. Now what I need to do is I need to find the smallest element to the right of AI that is also larger than AI. All right, so find smallest element to the right of AI that is at least as big as AI. Right? So AI, A3 here basically. Another color, oops. Another color, we'll go with red here. That's my guy right there, 3. So what I'm going to do is I'm going to look at everything to the right of 3. And if it's at least as big, I want to find the smallest one. So 5 is at least as big. And so that's my current, it could be 5. Right? Now look at the next element, 4. 4 is at least as big as 3, so that's correct. That's a candidate there. But also it's less than 5, so I update that. Right? Now I've got the least among these things that is at least as big as this. Right? What about 2? 2 is not at least as big as 3, so it is not a candidate. At that point, I've found what I'm looking for. Right? The smallest element, bigger than 3 is 4. Right? So what I end up doing is I swap 3 and 4. And what does that look like? We're not done yet. So it's going to be 1, 6, 3, 5, 4, 2. I end up swapping these two. That gives me 1, 6, 4, 5, 3, 2. And remember, 3 is still my original AI over here. Right? The last operation to get to the next permutation is we sort the elements to the right of that swapped element. So in other words, we look at everything after this and we sort. Right? Well, there's only one element, so trivially we're done. Right? And the next permutation is in fact 1, 6, 4, 5, 3, 2. Right? 1, 6, 4. Oops. 1, 6, 3, 5, 4, 2. 1, 6, 4. I think I screwed up. Three, 5 is the last pair. 4 is the minimal element. So swap 3 and 4. We did. Giving us. Oh, sorry. Let me go ahead. Let me go ahead and back up here. All the way over here. What I meant to say was the swapped version. So this is going to end up going 1, 6, 4, 5, 3, 2. This is, let me label this a little bit better. This is A prime. A prime ends up over here. And so this is what we end up sorting. Right? Once we've sorted that, then we get 1, 6, 4, 2, 3, 5. Right? This ends up being sorted. There we go. Sorry about that. And 1, 6, 4, 2, 3, 5 is the next one. Let's do one more since I screwed that up. 1, 6, 4, 2, 3, 5. 1, 6, 4, 2, 3, 5. All right. So first step is find rightmost pair such that a sub I is less than a sub I plus 1. Right? Well, what about this? Immediately you stop because 3 is less than 5. So there is, unfortunately, it's probably not going to be all that interesting here because the next operation is going to be what? Find the smallest element to the right of 3 larger than 3. And it's not going to be all that interesting. Why? There's only one, 5. And so what we end up doing is we swap 3 and 5, and then we sort to the right of 5. Right? So it ends up being, swapping is 1, 6, 4, 2, 5, 3. And then we end up sorting 3, but it's by itself. So 1, 6, 4, 2, 5, 3 is the next one. Let's try to do it one more time to see if we get something that's a little bit more interesting here. All right, so find rightmost a sub I less than a sub I plus 1. So I'm going to look at these two. Well, the inequality does not hold for 5, 3. So we look over here. 2, 5. That holds. And so 2, 5 is the pair that we're looking for, and a sub I ends up being 2. Now we need to look find the smallest element to the right of 2. In other words, we're looking over 5 and 3. That is greater than 2. Well, they're both greater, 5 and 3. So we end up with 3, right? And we swap them. We swap 2 and 3, and that'll end up giving us 1, 6, 4, 3, 5, and 2. Remember that this is our A prime. So what we need to do is we need to now sort to the right. 5 and 2, that ends up, well, they're out of order, so we do end up changing it. 1, 6, 4, 3, 2, 5. All right. All right. Anybody, if you want to see one more iteration, we can. But otherwise, I was going to use the last 15 minutes or so here to actually program this to get more experience here with Python. Right? So I've already imported copy over here. Give me a second. There we go. All right, so what we're going to want to do is we're going to want to generate permutations here. All right, so let me set it up for n to be 5. There we go. And so I've created a permutation. Before we were going 1 through n. Now I'm going to be going through 0 through n minus 1 because, of course, Python uses 0 indexing. And we're going to design this similar to what we did yesterday by creating a function that we give it the current permutation. It runs this algorithm we just developed, returns a new deep copied permutation, and we'll print it out, and then we'll simply pass that in again to get the next one. We're going to design this such that when you get to the end of the algorithm, there are no more permutations, so it returns the last one. Right? By the way, when is that going to happen? Well, if you've got, say, 1, 2, 3, what's the last permutation? It's when it's been reversed, 3, 2, 1. Or in this case, 5, 4, 3, 2, 1. Or 0 index, it's going to be 4, 3, 2, 4, 3, 2, 1, 0, right? All right. So let's go ahead and define this function. It takes a permutation. And I'm going to immediately copy that over so that I'm not touching the original permutation. All right, and then I'm going to start at the left, find the last pair a sub I less than a sub I plus 1. Right? So, a pair such that. Right? So to do that, first of all, I'm going to need n eventually. So that's going to be the length of the permutation. That's the number of elements in that list. And I'm going to start at n minus 2. Remember, I'm adjusting everything by 1 because of 0 indexing. If you've got 5 elements here, this is 0, 1, 2, 3, 4. I want to start here because if I started here, I would be comparing it to a sub I plus 1, which does not exist. So I want to start here so that I have something to actually compare to. Right? So I'm going to go into a while loop here while the permutation or the result of I is greater than or equal to permutation of I, or result, excuse me, of I plus 1. Right? And why did I reverse that? Remember, we want a sub I less than or strictly less than a sub I plus 1. And this should be in parentheses, in brackets here. I'm going to go down. I'm looking at this one. That's not it. I'm looking at this one. That's not it. I'm looking at this one. Okay, there. That's that pair, right? I want to keep going down by decrementing I. Remember, you cannot do something like this with the decrement operator. You just need to go I minus 1. Right? After I break out of this while loop, I've found the pair that I'm looking for. I'm referring to this one, and then this one is strictly less than the one right next to it. Right? And by the way, before we continue, what if we fall off the face of the list? What if there is no such pair? Right? Remember, 5, 4, 3, 2, 1. Then we've fallen off. Right? There is no pair such that that inequality holds. That means that we're done. And we can incorporate that into our method here by checking. If I has gone off the deep end, then we'll return none. There is no next permutation. Okay. Otherwise, I'm going to start at I plus 1 for another what I want to do now. Sorry, let me go ahead and rephrase this. We found the pair such that the inequality holds. Now I need to look at all of the others and find the one with the minimum value that is also greater than this one over here, right? And you could probably come up with an easy list comprehension if you are an advanced Pythoner. I'm not, so I'm just going to write a traditional loop here. What I'm going to do is this is my a sub I. I'm going to start over here and assume that this is it. Because that inequality holds, I already know that this is going to be greater than this one over here, right? So I'm going to start there and try to find something larger. For k in the range of I plus 1 up to n, but not including, if the result of k is less than what we've found so far, right, then we found something smaller. But we also need to make sure that it is greater than the original one over here, a sub I. So we need an and. Result sub k is greater than result sub I. There we go. Then we update. I'm just going to update our index variable here, j. Right? J gets a value of k. Right? So let me put that into the notes here. J is the index of the minimum element to the right of I that is also greater than result sub I. Okay. And now we do our two operations. We need to swap a sub I and a prime, right? Remember that we've called now here a sub j results of j is our a prime, right? So I need to swap them. Here's a cool Python tip, I guess, right? I could, of course, create a temporary variable, have 3 lines of code where I put one into the temporary variable, the other back into the original, and put the temporary back into the second. Or I can use a compound assignment statement. So result sub j is equal, and comma, results of k, sorry, I, is equal to results of I, results of j. There, that's correct. That's correct syntax, right? I've got AB is equal to BA, right? Cool little trick. You can swap those directly, right? Why? Because on the left-hand side, basically, this is kind of just a tuple that's been uncoupled, or whatever their terminology is, and the same thing on the right-hand side, right? So I've swapped those. Now I need to sort the result, but only on elements j plus 1 through n minus 1, right? In other words, I swapped them, and now I need to sort these guys over here, right? You could dump it to another list, sort that list, and then put it back on. There are lots of ways that you could do this, but the easiest Pythonic way of doing it is to do a sublist, right? So what this is indexing, right? The result of j through n exclusive is going to be sorted of the results of j through n. Right, there we go. Sorted is the built-in sorting algorithm that you can sort any list the default is in ascending order or non-decreasing order. And so what I've done is I've left the left-hand side of the list alone, and I've only specified I'm going to change j through n minus 1 over here, and I'm going to reassign that by handing that sublist off to another function called sorted. It's going to sort it, and then I'm going to put that back and tack that back onto the end. It's not really all that efficient. If this was a very large list, I probably wouldn't do this, because I do believe that it results in a copy, right? It chops it off, throws it away, deletes it, and dumps it to another list, hands that list off. It does get sorted, I think that is by reference. But then I tack it back on. It's not in place, basically. It is destroying and recreating memory to do this, but syntactically, that's beautiful, right? But it is definitely not the most efficient way of doing this. And of course, at the end, I need to return the result. Right? So let's go ahead and see if this works now, if I didn't screw it up. All right. There should be 120 permutations, 5 factorial. We start out with the identity permutations, 0, 1, 2, 3, 4, and go all the way to when do we end? We end when everything has been reversed. 4, 3, 2, 1, 0. If you walk through the algorithm, these two do not meet that inequality. It's got to be strictly less than. These two do not, because they're out of order, and out of order, at which point we're done. There's no other permutations to consider. Right? So that's how you can generate permutations. Of course, it's going to be super exponential, right? Let's go back over here to the iPad. It's why generating permutations is super exponential. In other words, it's even greater than 2 to the n. That's exponential. This is going to be order n factorial, because that's how many permutations there are. Even for a small graph, like say 30 nodes, right? 30 factorial, nope, you're not getting that done anytime soon, right? So is there a better way? I hinted at it when we looked at this graph, right? That if I were to naively generate permutations, right? Let's see. Let's go with this color here. A, B, C, D, oops. And then go over to D, right? That's not a valid edge. Why did you bother even generating this permutation when it doesn't even lead to a valid a path at all, right? Instead, what we're going to want to do is we're going to want to focus to identify a structure of the problem, and in this case, that has a direct translation to the structure of the graph. I don't have to consider any permutation that has DC in it, right? In general here, there are going to be 1, 2, 3, 4, 5, 6. There are going to be 6 factorial, or that's 720 possibilities. If I were to consider every single possibility. But I don't need to consider any possibility in which there's CD or, because it's undirected, DC, or, right? Because that edge does not exist at all. If I can take out those two things, that actually leads to, I can prune those out and not even consider any permutations that contain those pairs. And I've already cut it down to, I think, 4 factorial. Right? Or, yeah, they're about, right? Anyway, I've cut out a lot. There are lots of missing edges, though, right? There's not an edge from B to F. There's not an edge from A to E, right? I can cut out a lot by simply just paying attention to the actual structure of the graph. Treating it like a maze, right? When I am at a particular vertex, when I'm at a particular vertex here, I don't immediately say, oh, B, I can go to F. No, you can't, right? But I can go to A, I can go to D, I can go to E, and I can go to C, right? I cut out those choices immediately. And that's what I was getting, That's what I was getting at with this graph over here, right? If you actually do what is called a graph walk, you start at a vertex and then you explore the neighborhood. And then once you get to that neighbor, then you explore its neighborhood. Then you can actually cut out a lot of these invalid, infeasible solutions. That's where we'll pick it up tomorrow. Right? Hope to see you in office hours.